colleghi di altri gruppi, del nostro gruppo di astrofisica e studenti per essere qui. È un onore per me presentarvi il professore Luciano Rezzolla, che è scienziato di fama mondiale, che è stato fatto un ottimo intervento ieri per tutta l'università per i ragazzi, di cui mi ha chiesto prima i ragazzi e poi anche tutti quelli del dipartimento, e così ho organizzato questo meeting. Luciano è nato a Milano e ha i suoi origini pugliesi, ha studiato sia all'Università di Bari, ma poi a Trieste, ha fatto il dottorato a Trieste, ha volato negli Stati Uniti, è tornato in Germania, altro posto in Germania, quindi ha viaggiato un sacco, perché questo fanno gli scienziati sempre. E poi finalmente è arrivato all'Università di Allegheny University, dove è chair dell'Istituto di Astrofisica Teorica, quindi dirige il suo gruppo di dottorandi, molti, di visiting e di postdoc. Ha vinto numerosi premi per la sua ricerca sulla gravitazione, sia per quanto riguarda proprio la gravitazione in sé, in campi, quindi le equazioni di Einstein nel vuoto, che per quanto riguarda anche l'evoluzione più magneto-idrodinamica di questi oggetti come buchi neri e stelle di neutroni, tra quelli che vedremo oggi. Ha vinto numerosi premi e sostanziosi finanziamenti da parte del Consiglio, dell'ERC, proprio per i suoi progetti. I suoi progetti sono a metà strada tra fisica teorica, simulazioni e osservazioni dirette. Infatti famoso il suo progetto del Black Hole Cam, dove hanno cercato di prevedere un po' com'era l'immagine la cosiddetta immagine del millennio, con delle simulazioni numeriche. E quindi oggi ci parlerà di una cosa diversa dai buchi neri, della collisione di stelle di neutroni. Ho la fortuna di lavorare con Luciano da qualche anno, quindi anche i miei studenti sono stati lì in visita da lui e così mi ritengo portatore. Smetto di nuovo di annoiarvi in queste introduzioni e lasciamo spazio al professore Rezzolla. Grazie.
Thank you, Sergio. Thank you all for doing this. I've decided that to speak English, partly because the slides are already in English, partly because of our guests, and also because since there are so many students, you should get used to the idea that science is discussed in English. English is a science language. So today I will be talking about something which is very different from what I talked yesterday. Yesterday was supermassive black holes. Today I will be talking about binary neutron stars. It looks very different. Mathematically, as you will see, the equations are essentially the same. That's why I can use my expertise in both fields. So this is what I will be talking about. First of all, I'll tell you about the richness of binary neutron star mergers. I'll tell you about this funny idea of gravitational wave spectroscopy, how you can understand the equation of state, EOS, from the frequencies, and I explain what these frequencies are. I will tell you about two objects we have seen, GW170817 and GW190814, and the concept of maximum mass. For those of you who know what is the maximum mass, for those of you who don't know what is the maximum, I will remind you that. And for those who are more interested in particle physics, I will tell you how you can use binary neutron stars to probe the phase diagram of QCD and signature of the quark-hadron phase transition. And this is the last point I will touch over, hopefully on time, and it's about some generic considerations about a very simple concept, that is of the sound speed in neutron stars. And how, if you do things systematically and carefully, you find some new surprises. So, first of all, I am a theoretical astrophysicist. I really feel more in the gravitational sector, and to me, a binary neutron star or a binary black hole is a binary problem. So by that, I think about it as a scattering problem. I take two objects, I define an interaction, gravity, I assign some momenta, linear momenta initially, such that the stars have actually almost quasi-circular orbit, and then I let the Anson's equations do the job. And what you get out of this is a scattering problem, as I mentioned. So you start with two black holes, and you end up, as the result of the scattering, with a black hole with a mass which is slightly less than the mass of the two black holes, plus gravitational waves, and that's where all the extra mass or the missing mass is actually gone. We were able to do this type of calculation already in 2006, and in 2015 there was this detection that we actually saw. And you can see here, these are numerical relativity simulations. These are kind of simulations we were able to do already 10 years before, and they match pretty well with what we observed. So this was a great success for us. Now, if you think about binary neutron stars, this is also a very similar problem. Okay, you can think you start now with 2 neutron stars, and at the end of the day, you end up again with a black hole plus gravitational waves. However, there are 2 important stages in this process. The first one is that you do not normally produce a black hole. What you produce is a hypermassive neutron star, or HMNS. This is an object that shouldn't exist in nature. In fact, you can only produce it through a catastrophic event. You cannot produce it out of quasi-stationary changes of equilibrium. And in fact, this is a metastable object. This object will collapse pretty quickly. When it collapses, though, some of the matter in this hypermassive neutron star will be on stable orbits of the newly produced black hole. So you don't produce a black hole in vacuum, you produce a black hole in surrounded by matter. We call this matter torus, so you have a black hole plus torus. This torus is also unstable because there is a magnetic field that drives an instability, and so this torus also accretes onto the black hole, and that's why at the end of the day, you end up with a black hole plus gravitational wave. End of the day means a couple of seconds. All of this happens over a couple of seconds. And these stages are the most interesting and most difficult to study, because this is where all the microphysics is involved, but it's also where all the rewards are. Because if we understand the first part, the HMNS part, and as I will explain, there are ways in which we can understand what is the equational state of neutron stars. We don't really know what is the right equational state for neutron stars, and this is, I will show that there is a way of using observations to deduce that. The second part is also very important, because if we understand what happens in the second part, we possibly can understand what produces gamma ray bursts. For those of you who are not familiar with these, gamma ray bursts are the most powerful explosions we see in the universe. We see them from very distant corners of the universe, very high redshift, we say. We know now that they are associated with binary neutron star mergers. Okay? Whenever 2 neutron stars merge, you produce a gamma ray burst. But how do you go from a binary merger to a gamma ray burst? That's still pretty unclear. And then there is an important side effect, which is very important in my view, and that is, imagine you are smashing 2 objects which are a mass of more than a solar mass near the speed of light. You have so much kinetic energy that some of the matter involved, although the gravitational fields are strong, some of the matter is gravitationally unbound. It's a teeny tiny amount. It's maybe 0.1% of the total mass, but that is very important because that's very neutron-rich matter. This will undergo nucleosynthesis, heavy element nucleosynthesis, and so elements that you have right now on you, gold, all the gold that you have on you, is not produced in stars, it's not produced on Earth, it's actually produced by neutron star merger. So it's pretty clear the neutron star merger can produce gold. It's not clear they can produce coins, but it's pretty clear they can produce gold. So all of these things you can study by just studying neutron star mergers. And how do you do this? Well, this is the beauty of how you study these objects. You have to go to the blackboard and solve equations. These equations over here, we already seen yesterday. Well, these are, conservation of energy momentum, conservation of rest mass. You need an equation of state. This is where a lot of microphysics is contained. And then on top of this, you have to solve the Einstein's equation. And the right-hand side of the Einstein's equation is the energy momentum tensor. And the energy momentum tensor is a combination of all the things you put in your physical description. If you have a simple fluid, you have a fluid energy momentum tensor. If you have an electromagnetic field, then you have an electromagnetic component of the energy momentum tensor, which means you have to add the solution of the Maxwell equation, and then you end up with the magneto-hydrodynamic equation. If you have radiation, radiative losses, in particular neutrino losses, then you have an associated energy momentum tensor of radiation, and so on and so forth. And you have to solve a new transfer equation, radiative transfer equation. So all of these equations are the ones you have to solve. They look very beautiful and compact. Just to give you an idea of the way they look, once you start opening them up and putting them in a code, they look this awful mess of tensor equations with indices and second derivatives, and something that yeah, it's not particularly pretty. It's much prettier to see them in a tensor form. But this is the way you have to feed them and solve them in a numerical code. And if you spend and invest a good decade of your life into developing a code and solve those equations, this is what you will do. This is an example coming from one of our codes called Whiskey THC. It's possibly one of the most advanced generativistic hydrodynamics code. We're using a purely realistic hot equation of state. You see that initially the two stars are spherical, then as they get closer, they get deformed, they merge, they produce at this point hypermassive neutron stars. By the way, this is the density. This object is spreading a lot of matter, as this funny peanut shape with an LM equal 2 deformation. It's losing a lot of angular momentum through gravitational waves, spinning faster, and at one point it collapses, produces an event horizon, actually an apparent horizon, which is that gray ball over there. So this looks like computer graphics. It's not. It's really the solution of those equations that I've shown you before, done in full 3D. And this density that looks, a bit fuzzy, actually it's very high density. You're looking at 10 to the 8 grams per cubic centimeter. So if you have to remember something about what happens in a binary merger, that's the basic picture you have to have. You have a merger, you produce an hypermassive neutron star, and eventually you produce a black hole plus source. This is 99.9% of the situation. This is what happens. Okay, and the time scale for this to happen is between a fraction of a second to about a few seconds. Now, if this is the basic picture, merger hypermassive black hole, there are important differences. The first one is the total mass. It's easy to imagine. If you have two stars that are very massive to start with, the merged object will be very massive, and this will not survive for very long. Maybe will never survive. It will just produce immediately a black hole. By contrast, if you have very light stars, then maybe the merged object will be stable and will never collapse to a black hole. If you look at the typical masses we know neutron stars come with, and the maximum mass we know about, we expect in general that a black hole is formed. Another important aspect is mass asymmetry. In the simulation I've shown you, the two stars have the same mass, but this is not what happens in nature. In nature you have that the masses are slightly different. The mass ratio is not usually different, maybe 0.9, 0.8, but it's important. So this is a simulation where I show you what happens if you have a different mass. So these objects differ in mass by 20%. Which one is the more massive object? A question for the student. The left or the right? It's easy. You can see it from there. Just no. It's easy because you can see the contours. Okay, the contour. You see there is a little yellow contour, and in this regime, the more massive, the more compact you are. In normal stars, the more massive you are, the bigger you are. But if you are in such a strong gravity regime, it's the other way around. So keep an eye on the small guy, because the small guy is the one with lots of gravity. What it will do, it will strip its companion of its mass, it will tidally disrupt it, will accrete a lot of mass, and will produce very rapidly a black hole. So again, this is an example of what you can do with those equations. And the beauty of these simulations is that allow you to analyze this in a very high detail and with very high realism. Okay? What you learn from this is that actually having an equal mass is good because you produce tori which are bigger, more massive. You can put more mass into this tori, and so you can have a better recipe for gamma ray bursts. Gamma ray bursts, essentially, you can think that they exploit the energy in the torus to launch a jet. And the more mass you have in the torus, the better, more energy you have at your disposal. It's like putting money in a bank. The bank here is represented by the torus. What are the other degrees of freedom? Well, the equation of state is very important. Different equation of state will give you different answers. Magnetic fields are very important if you want to do a gamma ray burst. Radiative losses, neutrino losses are also very important. Again, you will subtract energy and momentum from the system in a very sophisticated manner. And our codes can do all of these things. Okay, so our codes have all of these different layers, And I'm not going to show you the fancier simulation with all the layers in. Rather, I will concentrate on some aspects so you can understand, better the single effects that come with any of this. So just like I've shown you with mass of symmetry, what happens when you have mass of symmetry, I will now show what happens if you have an equation of state. By the way, equations of state in our jargon are called stiff or soft. Does anyone know why they're called stiff or soft? Okay. So a soft equation of state is an equation where you can compress matter to a higher degree. By contrast, a stiff equation of state is where you can't compress a mass to a large degree. So take the same mass, a soft equation of state will give you, say, 1.4 solar masses. A soft equation of state will give you a 10-kilometer star. A stiff equation of state will give you a 14-kilometer star. So it's harder to make small stars if you have a stiff equation of state. So in order to understand what is the impact, and therefore the gravitational wave spectroscopy, I need to explain how the gravitational wave signal looks like. So this is a typical gravitational wave signal from a binary neutron star merger. And there is an in-spiral part with a chirping signal. You see that the amplitude is growing, the frequency is also growing. Then there is a transient over here with a few milliseconds. Then there is this hypermassive neutron star which can last tens of seconds. And then there is a black hole ring down. This is when a black hole is formed. The gravitational wave signal shuts off exponentially fast. This signal has to be compared with a binary black hole's gravitational waveform. As you can see, in the binary gravitational waveform, there is just a red and blue. And that's because there is just in spiral and a black hole ring down. A new black hole is formed essentially in a dynamical timescale. So all of this part here is what is missing in binary black holes. And this is where all the information comes. Now, something you can easily appreciate is that this signal is higher frequency than this signal. Just count the number of peaks per unit time, and you will see that this is a higher frequency signal. Now, this is the kind of simulation one can do nowadays, and this simulation was done a few years back. It took us more than a year, or actually not more than a year, but almost a year of supercomputing time, and I can explain all there is to learn in less than a minute. Okay. So different colors are different equations of state. Different columns are different masses. So this is low mass, this is a high mass. The top is a soft equation of state, the bottom is a stiff equation of state. You can immediately realize that a soft equation of state has a post-merger amplitude which is smaller than the stiff. Okay? In fact, this one is a fraction of the pre-merger, while this one is maybe half of the pre-merger. That's because a stiff equation of state, as I said, you can't compress it a lot. It means you have an extended object, and this extended object will produce a lot of gravitational wave. It would be a very efficient source of gravitational wave. Don't forget, gravitational waves go like the second time derivative of the mass quadruple. You have big object, you have a large mass quadruple. You can also see that a soft equation of state has a signal that is at a higher frequency than the stiff. Okay, here you can still see some white in the post-merger. Here there is no white, it's all a continuous red, and that's because you have a very compact and dense object which is vibrating at very high frequency. Another thing you can tell is that a stiff equation of state will very rapidly produce a black hole. This one is the highest mass, and at the end produces a black hole, while this one, which is an even larger mass, but is a soft equation of state, doesn't have any sign of wanting to collapse. In fact, this can go on for 100 milliseconds. So this is roughly a minute, and this is the most essentially what you can gain and understand out of this plot. But it becomes so transparent when you have all of this picture together. So sometimes collecting data in large amounts is necessary in order to understand better the detail. If you look at just a single of these waveforms and not the whole picture, you will not understand much. Now, imagine I take a Fourier transform of all of these signals. What you obtain is this. And I don't want you to pay any attention in particular to any of these panels, but just realize that these spectra have peaks, okay? And essentially these are lines. These are lines in a spectrum. And so
Is it a spectrum of the window?
I will tell you better in the next slide, but it is not, and I'll explain how. But you can see the continuous line is just a post-merger. Was there another question? No. So you see there are lines, and there are these peaks. And the idea is gravitational wave spectroscopy is exactly understanding where these peaks are and how they are related to the properties of the matter. And that's why I call it gravitational wave spectroscopy, learning from the spectrum what are the properties. If you followed astronomy, you know that astronomy has become a science when people have realized that stellar atmospheres contain absorption and emission lines, and by knowing where they are, you understand what elements are there. So in order to understand how this works, there's a huge bulk of work to which we have contributed, but there are many other authors who have also contributed. So take one equation of state, and it's called GNH3, whatever it is. This is a signal in time, this is a signal in the Fourier space. The dotted line is the in spiral, okay? The low frequency part. And this part over here goes like a power law here at very low frequency. Then you can see that the spectrum has three peaks. A first peak F2, a second peak F1, and F3. We didn't have a lot of fantasy when calling these peaks. But it's clear, if you've done a bit of Fourier transforming yourself, that this peak, F2, must be relative to this portion of the signal here, because it's almost frequency, it's almost single frequency, constant amplitude. So F2 comes from whatever happens between 5 and 25 milliseconds. Vice versa, F1 and F3, these are two sidebands that are produced in this part over here, between 0 and 5 milliseconds, and there is a very nice toy model that explains why you have these two sidebands. And this little dot here is the frequency at the merger. So it's a reference frequency. It's the frequency of gravitational wave signal at the time when they merge. Now, something else you have to appreciate. This is the sensitivity curve of advanced LIGO. This is the Einstein telescope. This is for a source at 50 megaparsecs, so extremely close. Too close to be real. What you would expect is that actually this line goes down below the green. In fact, this is too high frequency for present detectors to be. Now, let's change the equation of state. Let's have a soft equation of state. And I'm just aligning them at t equals 0. So you can see that the gravitational waveform is different. My pointer is gone. Okay, it's different here in the spiral. It's different in the post-merger. But if you look at the spectrum is also different, but has the same features, and F1 and F2 and F3. Okay? So what you learn from this is that by just knowing where the position of the lines are, you can tell something, because the properties that you have here now can be related to the properties of the equation of state. You can see very clearly that everything moves to the right. That means everything goes to higher frequencies. Soft equation of state goes to a higher frequency because you have more compact objects. Okay, you can see it clearly from here that the frequency is higher. And also the merger frequency is higher. Does anyone know why the merger frequency is higher? It's not difficult. Soft equation of state means objects which are closer, which are smaller. Okay. This means that the star will do maybe one more orbit, and so the frequency will go further up, and that's why they merge at a higher frequency.
They have less resistance.
Well, if you have a big object, they will merge when they have a large separation. If there's a small object, they will merge at a smaller separation. If you have black holes, they will merge at a later. And every time you get closer, your frequency goes up, so you can go to a higher frequency signal. So what is beautiful about this is that you can find universal relations, so the relations which are almost independent of the equation of state, that relate this frequency to properties of the equation of state. So just to give you an idea, you can relate the frequency F1 with the average mass and radius, which is a quantity well defined for each equation of state. these are all different equations of state, and in principle, all of these colored points would be scattered all over the place. Instead, they follow very tight relations, not perfectly. That's why they call quasi-universal. And so, in principle, once you measure this is a frequency you measure, it's a line, you have immediately a measure of the complexity. And you can do the same for F2 and F3. And there is a lot of tricks on how to use this to determine, for instance, how well can you measure the radius of a star once you have detected a post-merger signal. As I said, me telling you all about the post-merger signal just shows you that the theorist is an incurable optimist. I am telling you about what you can learn when seeing this frequency, but we haven't seen any of this frequency. And we probably will not see any of this frequency up until we get to next generation detectors, because, as you can see, we're looking at 2.5, 3 kilohertz. This is far more than what LIGO or Virgo can probe. Okay, I will now go to the next topic, which is these two objects and the concept of maximum mass. Who knows what is the maximum mass, or who doesn't know what is the maximum mass? You don't know. Okay, very good. So I will be a bit pedantic and remind you what is the maximum mass. So what we know is that GW17 at this mass over here, 2.74 plus a few percent. And out of this, you can tell, or you can set a limit on the maximum mass. What is the maximum mass? Take the Einstein's equation for a self-gravitating, isolated fluid object in spherical symmetry, non-rotating. Then what you obtain are what they call the TOV equations. These are a set of ODEs. You solve them, and you obtain a set of solutions like this. So you have the mass increases as a function of central density up until you reach a maximum. And this is the maximum mass. So that's the maximum mass. It's a very generativistic effect. It doesn't exist in Newtonian gravity. That's because beyond a given mass, you cannot produce an object which is stable. In fact, anything to the right of MCOV is unstable, dynamically unstable, will collapse to a black hole. Now, this is a bit of a funny plot because there are no numbers. And the reason why there are no numbers is because every equation of state will have a different maximum mass. So MCOV will go to the right, to the left, up and down, depending on the equation of state. That's the difficulty of determining what is the maximum mass. You can find more solutions for self-gravitating systems, in particular if you start spinning them up. These are rotating stars, and all of this green region is called the region of solutions of uniformly or rigidly rotating stars. And the space of solution is upper limited by this line over here, which is called the Keplerian limit. So any star sitting on this black line is spinning at the maximum frequency possible. You spin it up a bit more and you will break it. You will start losing mass at the equator. And you can show that also this sequence has a maximum, and that these two maxima are related by a line which is called a stability line. And you can show that anything to the right of this line will collapse to a black hole. Anything to the left is stable. You can really do this experiment with our code. You take a star, you put it here, and it will collapse. You keep it here, slightly different central density, and will stay there forever. Now, of course, we don't know also what is the maximum mass of rotating configuration. However, and here is an important result, there is a relation which is universal between Mmax and MTOV. So independently of what is the equation of state, you know that you gain 20% in mass if you rotate at the maximum speed possible. Okay? This is actually this is a result that I obtained with a bachelor student. Okay, so bachelor student can provide very influential papers. So this is what we found. There is more solutions. Okay, this is just an addendum. Let me go back. It's 1.2. Okay, we were using a set of equations of state to derive this. It was about 30 equations of state in 2016. We have repeated the same analysis with far more equations of state, with millions of equations of state, and we have improved this which is 1.25, but this doesn't really change much what I want. So there is just a 4% difference, but this doesn't affect really what I want to say. Let's go back to the space of solution. There are more solutions in this space. You can go above the uniformly rotating stars, but then you have to start being in differential rotation. So in this region, you are differentially rotating stars. Okay, so the sun would be in this region. And again, you can show that there is a stability line, and you can show that if you are to the left, you are stable. If you are to the right, you are unstable. Okay. So now here is the logic. GW17017 must have produced a differentially rotating star. Okay, because inevitably when two stars merge, you can't have immediately uniform rotation. There must be differential rotation. So in the space of solution, this is where they were. Yes. We also know that there was a gamma ray burst associated with this. This means that a black hole was produced. And this means that somewhere this guy has gone from here to the right of this line. And there are two options. One is following path 2, or the other one following path 1. If it followed path 2, it collapsed while being still differentially rotating. It is still in the pink region. If it is instead went into the green region, then it collapsed almost as uniformly rotating. And we think it cannot be 2, because 2 is very rapid. You've seen the first animation, okay? You collapse to a black hole and you are still differentially rotating if you collapse in the order of few tens of milliseconds. Because after 10 milliseconds or 20 milliseconds, you essentially become uniform rotating, at least in the center. But we've seen a lot of kilonova emission, a very bright kilonova emission. That means a lot of matter was lost by the remnant. And this means that the remnant cannot have collapsed immediately. They must have been surviving for at least a second. And so it must have followed this path number 1. Okay? So this is what you can deduce. So number 1 is much more likely because of the large exacting mass. Okay? So essentially, we now know that GW17017 must have entered in the green region and collapsed very close to M max. Okay, so you consider track number 1, and you know what is the gravitational mass of GW17017. You remove the mass from the kilonova emission, you use universal relation, and you have now a new upper limit on the maximum mass. So this we already know, and this is firm and solid, and no one can debate this, because we see stars which have at least 2 solar masses, and this is the new upper limit that we have established in 2018. And if you are not convinced by my logic and my line of arguments, fear not, because the very same result, of 1% difference, was obtained by other groups following different routes. So maybe my line of argument is wrong, but my result is right. And so, according to this picture, the largest possible mass is 2.33. Okay, because that's 2.16 plus 17. So this is a paper that has seen a lot of attention. We were very happy. Up until this guy came along, GW190814. So 2 years later, we saw this object. Very bizarre. This one has a mass of 22, obviously a black hole. This guy has a mass of 2.5 to 0.6. So if this is a neutron star, all I've been telling you for the last 15 minutes is wrong, because I've said you cannot have more than 2.3. Okay? So how do you resolve this tension? We don't know whether this is the smallest black hole or the heaviest neutron star. We can't tell this because the signal wasn't long enough to be distinguished. And so if it was a neutron star, as LIGO considered a possibility, then all of what I said is garbage. We can't use, there was no electromagnetic counterpart, so I cannot use any consideration about kilonova and exacting mass. The only thing is, either you live with the doubt, or you maybe consider the different options and try to solve the tension. So how do you solve this tension? The first thing is, well, let's consider what happens if it is really more than 2.5. Is there anything that breaks in our understanding? That's what we've done. Essentially, we have built a simple model that describes all of the processes that go into this picture. You know, you measure a given mass, then you give a certain mass to the hypermassive neutron star, you lose a certain mass, you lose a certain mass in gravitational waves, you lose a certain mass in rest mass. And of course, we don't know exactly the all of the different coefficients, but you can make them as parameters. So this is a multi-parametric problem. You have 10 different parameters, and you can then solve this multi-dimensional optimization problem. And that's exactly what we've done. We use a genetic algorithm, which is a very interesting idea and simple to code. Essentially, a genetic algorithm is you have a multi-parametric system. You change one parameter. It is like having a genetic change. If this genetic change leads you to an improvement, you keep it as an improved genetic mutation. If it gives you a worse fit with the data, then you just throw it away and you have a new genetic modification. Okay, so it's very easy to code because the logic is very simple. And the first thing we've done is we tested the code with our prior, which is that maximum mass is less than 2.3. And this is, you know, the pink is the previous posterior, the previous guess, that the mass was between 2. Whatever it was, 2 and 2.33. And this is the posterior coming out of this analysis. You can see that now the posterior has a proper probability distribution function, but the probability distribution function fits exactly where we were estimating. So everything seems to be, you know, in agreement with previous results. What else? You can calculate what is the amount of radiated energy or mass, this is expressed in solar masses, as obtained from numerical relativity. Numerical relativity tells you that you can't lose more than, say, 0.15 solar masses. And you can think that this is mass is lost both in the inspiral, which is this distribution over here, and in the post-merger. You can see the post-merger really loses much more mass than during the whole inspiral. And the combination is given by this distribution, the dark black, and it's in good agreement with what you would expect from numerical relativity. So this test is also passed. You can ask, what about the ejected mass? If you have such a distribution in masses with an upper limit of 2.3, again you find this is what you know from should be ejected from GW17 and the distribution once again is compatible with that constraint. So 2.33 doesn't break anything. Then you have a different assumption. You try 2.4 or 2.5. 2.4 is orange, 2.5 is red, and what you find out is that you overproduce gravitational waves. You produce more gravitational waves than we have seen from the macroscopic simulations, and you underproduce ejected mass. And it is these two results go together because essentially you're allowing for very massive stars. These are very effective sources of gravitational waves. They collapse very early. They don't produce a lot of ejected mass. So while this doesn't prove anything, what that tells you is that 2.4 or 2.5 are breaking all the constraints that we know in terms of gravitational wave emission and in terms of ejected mass. So how do you solve this tension? Well, very simply. You just say that the second object was a black hole. Okay? There is no problem with that. And in fact, it also explains naturally why we didn't see an electromagnetic counterpart, because binary black holes do not produce counterparts. So that's our take. I still open a bet to anyone who wants to take it. The maximum mass is 2.33. You want to take it in that bet? No.
But did you try the black hole neutron star merger to see the spectra if they produce that very frequency?
So black hole neutron stars are very boring because most of the time either the neutron star is eaten alive. In this case, the neutron star is 10 times smaller in mass than the black hole, so it would be essentially absorbed like a point particle. Or if they are more comparable and the black hole is rapidly spinning, you break it into a torus, but a torus doesn't really doesn't emitting gravitational waves much, and so you really see a gravitational wave post-merger spectrum if you have boundary neutron stars, not if you have.
So that can discriminate with the modeling if you have some observation.
Yeah, but we don't see the post-merger, right? We just see the inspiral. Okay, so let me move to a different topic. For those of you who are more interested in particle physics, I am in Frankfurt. In Frankfurt, there is a very strong group doing QCD, and my colleagues in the same corridor like to think that the universe can be represented in a phase diagram, in a QCD phase diagram. So everything is here. So temperature versus chemical baryon potential. The early universe is here along the high temperature 0 mu b. Neutron stars are very cold but very dense, so they're sitting over here. Lattice QCD probe this type of region over here. Low energy heavy ion collisions probe this region over here. And neutron star mergers instead probe this region over here. So you have temperatures of the order of 70, 80 MeVs at density of 2, 3, 5 times that nuclear saturation density. And so you can think that you can use neutron star to probe this line over here. This is a phase transition line. We know that there is a critical point here somewhere. We don't know exactly where it is. And maybe there is a phase transition, a first order phase transition in this region over here. So it would be interesting to know if a neutron star merger can probe and give evidence about a phase transition. How do you do this? Well, you build an equation of state that is either fully hadronic, this is the black line, or has an unstable quark phase and is given by this branch over here. Okay, so on this branch you have stars which have a core which is made of quarks and a mantle which is instead made of hadronic matter. And then you can run simulations. This is one such simulation. This is a very careful simulation done by Lucas Vai, a former student of mine. So this is density. Now we will start seeing the quark fraction with this different color code. So you can see that somewhere, not everywhere, there are some quarks that are being nucleated. And then we can have a look at another quantity, which is the temperature, which is shown over here. So now you have this beautiful, impossible to read diagram that shows you temperature, quark fraction, and density. But it's still pretty, okay? Now, this is better seen in more quantitative plots. These are 3 different panels, 3 different times. This is 2 milliseconds after the merger, 15 after the merger. This is the temperature. This color code is the quark fraction, and each panel is split in 2. On the left you see temperature, on the right you see quark fraction, and then you have this isocontour of the density. So what you see is that at the beginning is a hot temperature, hot regions that produce quarks. But the quark fraction is teeny tiny, 10 to the minus 5, 10 to the minus 6. This continues. There's always this correlation between temperature and quark. So you produce quark there where the temperature is high. Think about the phase diagram. But then at one point you produce a lot of quarks in the core, in the center. So when the central part, the high density part, is involved in the phase transition, that's when the equation of state softens. You don't have a lot of pressure support, and so you will collapse. So how do you see this? You see it in terms of gravitational wave. So this is also a complicated picture. The black line is an hadronic equation of state. At this point, you should be able to read and understand this waveform. The red line instead is the phase transition, the waveform of the simulation I've just shown you. Shown instead in red and black again are the gravitational wave frequencies, and the blue is the phase difference between the black and the red. So what you can see is that in the spiral, the phase difference is 0. So they are identical. That means there are no quarks. That's natural. So there are no quarks. There is no difference in the equation of state. But after the merger, temperature rises. You start nucleating, producing quarks. This produces differences in the waveform. You see a dephasing. And then at one point, when there is a full phase transition, there is a collapse. So this is a way, a smoking gun for seeing that there is a phase transition. You look at the spiral and you think, oh, I understand everything. This equation state, blah, blah, blah. But then you would expect that the collapse happens at this time. Instead, you see that the collapse happens earlier. So the fact that it happens earlier is a smoking gun for saying there must have been a softening and therefore a phase transition. Okay, so this is essentially what I said in there. You have to think this in terms of gravitational wave evolution. So if you think of this cartoon where you have the time here and the gravitational wave frequency, you have that the frequency goes up and then it settles to the F2 frequency that I've explained. Okay, so this is what you can imagine is a spectrogram that LIGO has produced. Note that this is just a cartoon. Okay, there are no numbers here. Then there is another possibility, which is the one I've just shown you here. You have a phase transition triggered collapse. Essentially, you have the merger, then the frequency goes up. At one point, you have the full phase transition, and you produce a black hole. Another possibility is you have a phase transition at the merger. Immediately at the merger, in a dynamical timescale, the whole system is producing a quark core, and now you have the system as a higher frequency over here. And then there is another possibility, and it is what we call delayed phase transition, where essentially you have a phase transition not at the merger, a bit later, and then you have again an equilibrium with a higher frequency. So this is a cartoon to explain the zoology of possible behavior. We played around with this idea, without knowing any equational state. In particular, we have played around and shown that these are the class of possible behaviors. We have simulated this guy. Other people have simulated the green guy, and we have simulated also the orange. And this is an example of this. Okay, this is no phase transition. This is the typical spectrogram you see also by LIGO. This is the phase transition in this collapse. Again, no phase transition. And this is a delayed phase transition where you start with a given frequency and then you go up to a higher frequency. You can also see clearly from the waveform. So this is the most convincing, in my view, case of all of them, because if you look at the spectrogram, if you look at the spectrum, this is a fully hadronic spectrum. I already explained you have this big F2 peak, and now you have two big F2 peaks. One which is when the star was still fully hadronic, and one when the star is having a quark core. So this is the most convincing, in my view, smoking gun and evidence that a phase transition has taken place and that has led to a stable object. So if we will ever see this, we will see phase transition.
So this is with the same equation of state, correct?
No. These are different equations. One equation of state, one behavior. So we had to come up with different equations of state to see all the different behaviors.
Because if you mix all the possible equations of state together,
you know,
someone not well determined like observation, correct or not?
Well, the idea is that every equation of state will give you a precise
amount of work.
Yes, but also precise. So let me go back. Okay. Oh, sorry. Yeah. These are classes of equations of state. So this is an equation of state where you will have a prompt phase transition. This is an equation of state that will have a delayed phase transition. Then you can play around, and then you can have, whatever, something where the phase transition happens earlier or later, playing around. But these are still elements of the same class. Okay, class delayed phase transition or class prompt phase transition. More questions? Okay. I will now, how I'm doing with time. Okay. I want to, this is my last topic, then we're done. It's about the sound speed in neutron stars. So I'll try to explain that we don't know what is the equation of state. If you ask to a nuclear physicist, he would say, oh, I know what is the equation of state. The problem is that every nuclear physicist will have a different equation of state. So you don't really solve the problem. Really, the reality is that, depending on how you attack the problem and the level of approximations, you end up with significantly different answers. However, there are some firm points. Okay, something that we know has to be true. And this can be seen in this diagram where you have pressure and energy. Now, an equation of state is a line in this diagram, at least for some dummy like me in nuclear physics. To me, an equation of state is just a line. But this line cannot be drawn at random. It has to match two important limits. The low energy, this part over here where we think nuclear physics is very well known, okay? And the very high density, where QCD can be handled perturbatively, so the PQCD limit. And neutron stars are in this region over here, and most reach this density. So you see that this regime here is really out of question for neutron stars. Neutron stars will never probe. You can use nuclear effective field theory to guess a bit more, but here the uncertainty becomes rapidly very large. So what is in between this region over here? You can think there are infinite possible solutions that merge between this limit and this other limit. And that's exactly the approach we have taken. We don't know what is the equation of state, but we just know what are the constraints. So let's build all the possible equations of state till we get tired of them. And then we can answer some questions which are trivial but fundamental. Like, does the sound speed inside a neutron star behave monotonically or not? So the sound speed, if you have low density, will be very small. If you have very, very high density, it will reach the square root of 1 over 3. So c squared would be 1/3. That's called the conformal limit. Okay, ultra-relativistic gas has to be like that. And you can have, the solution blue, the blue solution, which is always subconformal. You can have the red solution, which is subconformal but non-monotonic, or you can have a superconformal and non-monotonic, which is the orange. And essentially, we don't know which one is right. But maybe statistically, we can draw some conclusions. And that's what we've done. We have built a lot of equations of state. What do? We actually start from the sound speed, and we give a prescription, a random prescription in the sound speed, as a piecewise linear prescription in terms of the chemical potential, which gives you then lines of this type in terms of the energy density, and again equations of state, and ultimately some mass radius relation. And then we check that any equation that we produce in this way is physically and astrophysically consistent. We make it physically consistent by checking that the sound speed is always subluminal. We make it astrophysically consistent, making sure that we don't get radii or maximum masses which are not allowed. And we do this for 15 million equations of state, and 90% of them we throw away because they violate one of the constraints, but we're left with 1.5 million equations of state. That's a lot. You can do statistics. And this is what you learn out of the statistics. Okay, so this is the PDF, probability distribution function of the sound speed. And it's very clear, if you look at the colors, that somewhere within the star, the sound speed must be superconformal. And in fact, you can calculate what is the fraction of possible equations of state that are always subconformal, and this is 10 to the minus 5 of the whole sample. Okay? So this is an interesting example of how, although we don't know the answer, we have very strong statistical evidence that the right answer statistically must have the equation, the sound speed being superconformal somewhere inside the star. You can, because you have so many equations of state, you can also draw probability distribution function about the radii. Okay, so this is again shown with this color code, and you can see that you can now make a cut in this posterior, and you can get what is the distribution in radii for say a 1.4 or a 2.0 solar mass equation of state. And you can see that 1.4, which is the typical reference mass, you have about 12 kilometers, plus or minus something. Okay? So that's our best bet. A 1.4 solar mass star will have a median radius of about 12 kilometers, plus a large uncertainty. you can also get a very important result, which is you can build a PDF for the chirp mass. The chirp mass is this strange combination of the masses of the binary, but because the phase evolution is expressed in terms of the chirp mass, you have that this quantity here is the actual measurement. Okay, gravitational wave measured this quantity to a very high precision, third significant figure. And what you find out is that the distribution function is very well contained by two curved dashed lines, which have, an analytic representation. You can fit some expression there. And important of this is that once you make a measurement of the chip mass, you immediately set a lower limit and an upper limit on the side of the formability. The side of the formability is this fantastic quantity that tells you how much you can distort an object under a gravitational field. Okay, this is a very important property of the equation of state, and you can see that essentially this is the chip mass for GW170817, 1.186. Okay, three significant figures, and LIGO had given up an upper limit of 720, which is perfectly compatible with our statistics, but we can also give a lower limit of 200. And now you can imagine any other chip measurement will give you a very small range in possible types of probability. So I personally find it a very powerful result. The final point is, okay, I've shown you that somewhere in the sound speed becomes larger than 1 over square root of 3. But where? It would be nice to know where. So how does the sound speed vary in a star? Is that the maximum at the center of the star? You may think naively that the sound speed is a measure of the amount of compression. A star which is more massive or is more dense at the center, so the sound speed must be higher at the center, right? This is a very simple line of logic. Does the maximum value attain a constant value? So these are very simple questions, basic fundamental questions, but finding an answer is very complicated because every equation of state will have a different maximum. And so, you have essentially that your space of parameters goes between 0 and speed of light. The radius will be between 0 and the radius of the star, and every model will be different. The mass will be between 0 and the maximum mass, which can go from, 2 solar masses to 3.5 solar masses. So this is all very frustrating. But what you can do is you can say, okay, wait a second, I don't care. Let me just write everything in a unit cube. So your unit cube now is sound speed versus speed of light, 0, 1. The radius, the radial coordinate versus the maximum radial coordinate, again 0, 1. And the mass versus the COD mass, between 0 and 1. And now you have a scale and EOS independent representation in terms of a unit cube. Everything has to be in this unit cube. So this is an example of what you can see. So this is again a bit of a complex. So let me just draw your attention. This is the sound speed in speed of speed of light. This is the radius as a function of the maximum radius of this is the center, while this is the surface. And this is the maximum the mass versus the maximum. So these are light stars and these are heavy stars. And the blue surface is essentially the median of the probability distribution function in this unit cube. Don't forget that this is all statistics, okay? So you can just derive statistical inference. But let's concentrate on a very simple question: is the maximum sound speed at the center or elsewhere? Well, what you find out is it is at the center. R over big R equal to 0 for up to very massive stars. Then at one point, for very large stars, it is not at the center. It's actually moving outward. And at the end of the day, for the most massive stars, it is actually at about 0.7 of the star. So it's really in the outer layer. You can best see this. These are sections that maybe help you see this. This is a light star, so maybe 1 solar mass. This is 0.75, maybe 1.4 solar masses. This is like 2.5 solar masses. You can see that the sound speed at the maximum at the center, while here the sound speed at the maximum somewhere at 0.7. Okay, so it is as if light stars, the sound speed is monotonic with a maximum at the stellar center, and heavy stars is non-monotonic. Actually, at the center is smaller than even the conformal limit, and certainly smaller than the one in the mantle. Now, you can also think and translate sound speed in terms of stiffness and softness. You can think light stars have a stiff core because the maximum is at the center and a soft mantle. And then heavy stars have the opposite, have a soft core because the sound speed is not very high, but have a stiff mantle. Now, these two results have appeared in two letters on RPJ, one after the other. They were really attached to each other. And we had to come up with a press release that was interesting and to understand. And so I came up with this analogy. Neutron stars behave like chocolate pralines. Okay? Well, if you want to capture attention, there is nothing better than chocolate. Light stars have a stiff core and a soft exterior, like this, that have a hazelnut at the center, while heavy stars are more like those chocolate, those pralines, where there is a soft core. And the main journal, one of the main journals in Germany, the Frankfurt Allgemeine Zeitung, has picked up on this press release and has defined the sweetest discovery of the year. Well, again, use chocolate if you want to attract people. Here's my conclusion. I've tried to explain what is there is a huge potential in understanding the equation of state from the post-merger peaks. These are quasi-universal. I've explained how using just two objects we have already set interesting limits on mass, maximum mass, radii, tight deformability. I've explained that a phase transition can occur and will leave a signature in gravitational waves. We don't know which one is the signature, but we have explored the different possibilities. And I've also explained that the sound speed cannot be subconformal and monotonic, and most likely superconformal somewhere in the interior. And last but not least, I've explained why small light stars are different from heavy stars. Thank you for your attention.
Question?
So the question on the first part you said, I know there are some sort of deep to the soft.
Yeah. Yeah.
Soft.
Let me get you to what you have in mind so that it's easier also for the others. Yeah, or you can also see here these feedings here. Yeah, with this one. Yeah, with this one, yes, indeed. So there are two, in all beatings, you have two frequencies which are very close to each other. And what are these two frequencies? One is the rotation frequency. This object is rotating, but it is also vibrating because the two stellar cores are still, wildly oscillating. And so this is why you and the softer the equation of state, the closer these two frequencies are. Instead, in a stiff equation of state, this beating doesn't exist.
A second question, sorry for my ignorance, but these merger of two neutron stars have been observed experimentally?
Yes.
There are observations also.
Yes, there are observations, but, well, now those two events which I mentioned, GW1708 and GW1908, but the only thing that we have seen is up to the merger. So just the low frequency of the signal. We haven't seen the post-merger because the detectors at very high frequency are not sensitive. So they disappear from the sensitivity of the detectors. And you need new generation detectors that are sensitive at 3 kilohertz in order to see this.
More questions? No. Young people. Go ahead. Your mom.
I can't believe you don't have questions.
Okay, he has a plane in a few hours, then we won't see it. Long enough.
Anyone wanting to go to an Erasmus must ask a question.
Thank you very much for the great talk. You just increased by orders of magnitude what I know about general relativity. But I thought you had mentioned earlier that you were going to explain how you do the transforms of these signals, because they're obviously non-stationary signals. So did you say, I think you had some more details about how you do the spectral decomposition?
Well, yes, this is what I was trying to explain in this in this illustration here. Okay, so this is how I tell you what are the properties of these peaks. It's obvious that this peak is part of this relative to this part where you have an almost constant frequency. Maybe the only thing which I haven't right told you is what are these two side peaks over here, and I can explain them easily because.
Is the signal on the bottom just a Fourier transform?
Yes, it's just a Fourier transform.
Yeah. You don't do wavelets or anything like that?
No, if you want to do a spectrogram, this is what we do here. Okay, if you want to do a spectrogram, like here, this is a spectrogram. You take a small window in time and a running window, and then you calculate what is the spectrum, and this is essentially the color coding of that spectrum. So the spectrum goes up in frequency and then stays around an F2 frequency. Okay, and in this case, my pointer is gone. Okay, maybe it's back. Yeah, here you see you have a first frequency here, F2, and then you jump to a new frequency which is higher. And this would lead to this spectrum over here. This is the first portion of the signal, the first portion in time, and this is the second portion in time. Okay? Yes.
I have a question. I have a question regarding the simulations of the neutron star mergers which you showed at the beginning of your talk. That is, we can see that after merging, the density is fluctuating quite a lot in the cloud of the material around the star. So, on the one hand, this is a good start for turbulence. But my question is there an idea of what are the instabilities which are at the origin of this strong fluctuation? When the two stars start to get closer, so you can have either maybe Kelvin Helmholtz or gravitational.
Yeah, so actually that's a very good question. You do produce a very strong Kelvin-Helmholtz at the merger because the stars don't hit each other head on. Actually, they rub against each other. So that's a perfect tangential discontinuity. You produce a lot of vorticity in that system, and this leads, because you already started with a strong magnetic field, you have a very strong vorticity, you produce a lot of toroidal magnetic field. Okay, you just have lots of vortices. Imagine you have colloidal, so the magnetic field is almost vertical, and then you convert it into a toroidal magnetic field. And this can increase the magnetic field by several orders of magnitude. How much? Well, this is what we don't know. What we know is that the initial magnetic field is of the order of 10 to the 10, because these are old pulses, and you should expect a gamma ray burst of 10 to the 16 Gauss. So you have to gain 6 orders of magnitude in a matter of a few milliseconds. Of course, if you have a Kelvin-Helmholtz instability, that's not a problem. But what we don't know yet from simulations is we can't reach a saturation, the saturated amplification, because every time you increase your resolution, you find a different saturation magnetic field. So what you can only expect is the saturation must be near equipartition, and this means 10 to the 16 Gauss. That's how you get 10 to the 16 Gauss. That's the first instance of turbulence. But then there is the upper-mass neutron star, which is rotating, is different in rotating, is still producing a lot of turbulence. And this turbulence we don't really resolve. Okay, we have resolutions of maybe 100 meters in the highest cases, and you would like to go to 10 meters or maybe to a centimeter in order to see the whole spectrum, MHD spectrum, which we don't. So this is a big question mark. That's why I'm here to learn from Sergio how you solve this problem in solar physics.
What is the overall size of the region that you're simulating?
Well, this is a tricky question. The whole size, because we have to capture wave. Okay, so the whole size is a few thousand kilometers, but the action in terms of gravity happens in about 100 kilometers. Okay, so you have to have a very far away, maybe 5,000-6,000 kilometers outer boundary, so you can capture gravitational waves. But the outermost regions of the star goes maybe 100 kilometers. The real star is maybe 15 kilometers. Okay, so there is a large range in scale. You need AMR to do this. Adaptive mesh refinement.
You have most of the turbulence in between stars.
And you have the, yeah.
But where the magic is not black.
No, but it's
turbulence over turbulence. Question. Yes.
Is it possible to use your spectroscopy to possibly detect dark matter or even discriminate among models for the dark matter?
Yeah, that's a very good question. So we don't know what neutron stars are made of. Maybe they're made also of dark matter. Maybe dark matter has managed to accumulate in the neutron stars with accretion, and so you have an hadronic neutron star with a dark matter core. And you can show by perturbation theory, so without doing all these complicated simulations, that indeed the signal, if you have an oscillating star which is fully hadronic, or an oscillating star with a dark matter core, that the frequency will be different, because you will have a coupled system, dark matter and ordinary hadronic matter. So yeah, the short answer to your question is yes. In principle, you can see this. There are many simulations that are available. In fact, there is just one group who has been able to calculate, or has had the endurance to calculate this. And if you can show that depending on the properties of the dark matter, which is a big question mark, how do you model dark matter? But you can show that there's going to be a change. How big is this change? Not a whole lot. A few hundred Hertz. So not something that will be completely different. Something that you can easily confuse with the different equation of state. But yeah, in principle, dark matter can be seen. Even in the spiral. There is another question over there.
At some point you said that the radiation loss component, the energy momentum tensor, is important, is relevant for the simulation. And how sensitive you are to this quantity? I'm thinking, this is basically the main contribution is from neutrino loss.
Right.
Can you put a bound on the neutrino number?
Well, yeah, you can actually calculate the luminosity, okay, and you can get that the luminosity in neutrinos is the order of 10 to the 50 Hertz per second, so quite a very intense flux of neutrinos. And the luminosity, because when you talk about neutron luminosity, you have to think about which species, but roughly they're all the same, so maybe a factor of 5 at most. And the details of this luminosity then depend on the equation of state. Different equation of state will give you slightly different luminosity. But yes, you can measure this systematically through an additional radiative transfer problem.
Yeah, maybe you can also use that to put some bound on beyond model physics, like for instance, I'm thinking about emission of axion, very light particles.
Yes, well, so what is exactly the observable you have in mind?
Yeah, no. I mean the loss of mass, basically. So you have emission of these very light particles in the same way as you emit neutrinos and you lose mass. Basically, you will have another contribution to this piece of the energy momentum tensor. And if you are sensitive enough to put constraint on this piece, then you can also put ideally a bound on the coupling of this particle as well.
That's very good point. Yes, we haven't done this. Of course, we need to know exactly how how to do the radiative transfer for axions. Okay, that the neutrinos, we know all the weak processes that are involved. We can put them in on the right hand side, and we can tell you, what is the fraction of neutrinos that is trapped, what is the fraction of neutrinos that is free streaming. So there is a lot of weak force, microphysics that goes into calculating that. I don't know if we have all of this knowledge about actions. We don't know the cross sections of actions.
We have it, yes. Okay. Of course, parameterized in terms of unknown couplings, unknown bands.
Okay, but then if you have some bounds, then we can use these bounds to say what is the expected luminosity in action. Yeah, for sure. Yeah. And how would you detect these actions?
So
You wouldn't. You would just see.
You would have an impact on your.
Mhm.
It would have an impact on your gravitational wave, the waveform. You will have a loss of.
An additional loss. Yes. Yeah. 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 That's a good point. Yeah.
You have a question?
Yeah. Sorry. So if there's some magnetic fields or matter or something around this violent occurrences, would there be shocks and reconnection events and so forth produced that might accelerate high energy cosmic rays?
Yeah.
Do you look into that at all?
Not yet. Not yet. But let's see if I can. There is a limit to what I could present, but maybe I can. I have some. Okay, so as I said, we have solutions with magnetohydrodynamics. Okay, so here is an example of one such simulation where you are doing magnetohydrodynamics, and I'm showing you two scalar quantities. One is the magnetic field strength in blue and green, and the other one is the density in red and orange. Because these are two scalar quantities, if I put them on top of each other, you wouldn't see anything. So you have to imagine that there is a wall here between these two stars, and on one side of the wall I always show one quantity, on the other side I show the other quantity. So it looks a bit funny, but you understand what's going on. Okay. So the two stars merge, and when they merge, they produce a very strong wind of low density, highly magnetized plasma. Okay. That's what you see, because you see a lot of blue but no red. That means high sigma, very low density. At this point, you see a black hole has been formed. Okay, so not much has happened yet. Okay, so this is something that I did millions of years ago, but NASA picked it up, and so you can see this nice cartoon that NASA did about this. So you have a colloidal magnetic field, you have the merger, you see the global magnetic field, and then you have this tangled magnetic field at the merger. And then you continue the simulation for much longer. And what you start seeing is that you have some instability, most likely shearing instability that is growing the magnetic field. And you can see that the magnetic field will suddenly become white out of the color code. You also see that there is a clear, structure that is being produced on the polar axis. And that's because essentially on the polar axis you don't have any angular momentum. So matter, because it's still pretty much cold, can only fall. And when it falls, it brings along the magnetic field. And so you produce essentially a large dipolar magnetic field. So this is what I was showing you. Maybe it's easier to see in terms of magnetic field lines. You see, you start producing a large toroidal component, and you then produce this kind of dipolar jet structure. It's not really a jet in the sense that it's not an outflow. It's just a magnetic confinement. It's just the geometry that is right. And if you look at the energetics, how much energy is going out in Poynting flux, the time scales, these are the typical things you would expect from a gamma ray burst. So this was taken as the missing link between binding neutron star mergers and gamma ray burst. So the idea is that if the stars are magnetized, the magnetic field will first grow during the merger and the post-merger, and will acquire a dipolar structure, and then out of this dipolar structure you can launch a wind, which would be the jet we observe in the gamma ray.
So when you use an equation of state, Einstein is fluid, if you like. It is really purely fluid. So everywhere in your volume, you use an equation of state, right?
Mm-hmm.
So, but the neutron stars, I can believe that close to the core, the density is very high, and the matter, let me call it plasma, because it's very collisional. So there probably it makes sense on equation of state. But immediately as you go a little bit far from the nucleus, from the center, in the atmosphere of a neutron star, or it may be probably after the center of this, right? It's becoming very collisionless. So probably equation of state doesn't make any sense. What do you think about that? What's your comment on this? I mean, on the only on the atmosphere, on the external.
Yeah, you have to bear in mind the numbers. Okay, even the lowest density that we have in our simulation, the lowest density. So the highest density is 10 to the 15.
Okay.
The lowest density that we have is about 15 orders of magnitude less. That's the jump we can handle on our code, 15 orders. So it's 1 gram per cubic centimeter. And 1 gram per cubic centimeter is still, I would say collisional. You don't have, gram per, okay, you don't have interstellar densities of 10 to the minus 20 or so, where you would think a kinetic approach. But the equation of state is something that I take from someone else. Okay, someone else tells me this is the equation of state. Okay. This is how pressure changes as a function of density, energy density or temperature, electron fraction, and whatever other fraction.
So it's purely thermal equilibrium.
Yeah. So it's in purely thermal equilibrium, and it's something that I import. Maybe when they will have students. Then we will have a code that is able to handle also the kinetic regime at a very low density.
Oh, that's probably yes. Okay, but okay, thanks.
I have a technical question. In these kind of simulations, where are your boundary conditions?
Boundary conditions are at 5,000 kilometers, and the boundary
very far from everything we are seeing.
Yeah, absolutely. This guy is, I don't think I ever scaled it, but this guy is about 20 kilometers, 30 kilometers maybe.
And do you use an adaptive mesh refinement?
You need to have an adaptive mesh refinement.
Okay.
And we have seven levels of mesh refinement. Lisa, you have raised your hand. What is your question? I saw you raise your hand. Yes.
Any event that is the collision from has any of these events been observed? I mean, the collision, of course, but maybe of two neutron stars or of neutron stars or a black hole, and do the results, experimental results, are they in accord with the numerical result?
Yes, this is what this plot is showing you. Okay, so this is the famous GW1717. This event that we saw in August 2017. Okay, and this is the spectrogram. This is showing you the frequency evolution as a function of time, and you can see that you see this part over here up to this point, and then the signal stops. Okay, that's in spiral. And then the gravitational wave detector stopped seeing the signal. 1.74 seconds later, these satellites, Fermi and I can't remember, Integral, see an impulse of light in the gamma, and that's a gamma ray burst. Okay, so yes, we do see this.
But apart from these, publishing
more. So we haven't seen any. These are the ones that have been published. I'm not in the LIGO collaboration, so I don't know if they've seen more. They are taking data right now in this what is called the O4 run, the fourth running period, and they expect to see between 0 and 60. Okay, so far they have seen 0 because there was no main release, but yeah, that's the expectation. That over this run, which will last, until end of 25, I think, they expect to see maybe a tenth of these objects.
Maybe there are also lots of
No, you can't see them passively. You need to see them real time.
I mean, data are not analyzed yet.
No, right now they have analyzed all the data they've taken, and they are looking at almost in real time to the data.
Thank you.
Yeah. Of course.
How do you include the quarks in your computation? How do they change your?
So to me, it's an equation of state. It's just
It's just that one.
Yeah, it's just P is a.
You don't have anything exotic in your momentum.
No, because at the end of the day, quarks appear also as a the equation of state allows you to the equation of state. This is the black is the hadronic and the red is the one with quarks. Okay, so depending on what is the mass and the density and so on that you reach, you may be always in the full hadronic, and then as you go to higher or more compression, higher masses, then you end up in this region over here. And that's what happens in the core. Okay?
Okay.
Yeah. Okay.
So, thank you again.
Thank you for that. Prego.